Okay, so this is a discussion of lab 19. Okay, you're going to do two labs that are going to be kind of the opposite of each other. So in lab 19, you have a circuit that's already wired up, and you have to figure out what the count is going to be. When we do lab 20, it's going to be the opposite. They're going to give you a count, so they're going to say, I want a counter that counts 0, 2, 4, 6, 8, and goes back to 0. And then you have to figure out how to wire it. Okay? So really, I mean, it's kind of a neat way that we do it and figure it out. And there's some design work that needs to be done, which is what you're going to be doing in your tables. So don't just build the circuit, you have to fill out the tables. All you really need to know for this, however, is how the JK flip-flop works. So you need to know that if J and K are both 0, that's going to be no change. If J is 0 and K is 1, that's going to be a reset, so Q is going to be equal to 0. If J is 1 and K is 0, so this is going to be reset. Q is going to be equal to 1, which is a set. And if you have 1, 1, so 0, 0 is no change, 1, 1 is change, but we just call that toggle. But what that means is, if you have assuming the presets and clears are high, so you'll notice in this diagram I did not draw the clocks, and I did not draw the presets, and I didn't draw the clears. That's just so this diagram doesn't get too crazy, but you can assume that all the clears and presets are set to plus 5 volts, and that this is a synchronous clock. Okay? So if the output is 1, it's going to change to 0 when you clock it. If the output is 0, it's going to change to 1 when you clock it. So toggle just means it's going to go to whatever it wasn't before. Okay? So if we know how this works, we can figure this out. Now, this process is more tedious than it is complicated, because you're just going to do one thing, and then you're just going to keep doing it over and over and over again until you get the answer you want, or until you get the complete picture of what's going on, right? So for example, we know what the flip-flops do, right? Everybody's aware what the JK flip-flop does? Okay. So if, for example, if I start at a count that's, and I'm just going to pick 0, 0 arbitrarily for no other reason than that's just what I'm going to do. Okay, so the way you have to think about this is, if you know what's on all these outputs, then you know what's on all these inputs, right? Right? Because if you know that QC is 0, well then you know there's going to be a 0 on JA the next time it clocks, right? And if QC is QC naught, so this is QB naught and QC naught, I believe. So if QB and QC are both 0, that means QB naught and QC naught are both 1s, which means you're going to have two 1s on this AND gate, which means this is going to be a 1, so KA is going to be 1. So you're going to have a 0 on J and a 1 on K, right? So that flip-flop's going to reset, right? Which means Q is going to go to 0. Well, this is QA, so the next time I clock it, I know it's going to go to 0, right? But it's kind of tough to keep that in your head. That's why we have the table that they give you in Lab 19.3 and 19.4. So what you need to look at is, what does QC equal? Sorry. What does JC equal? What does KC equal? What does JB equal? What does KB equal? What does JA equal? And what does KA equal? The reason we want to know that is because if we know what's on J and what's on K, then we know what the flip-flop's going to do. And that's what we're trying to figure out, is what the flip-flop's going to do. Okay? So, JC is equal to QB. I'm going to use a different color. JC is QB or QA naught. So this is QB or QA naught. KC is QB naught. JB is QA naught. KB is 1. Those are easy because if it's 1, it's going to be 1 all the way down the table. You don't need to look at the circuit to see what's going on. JA and KA are, so JA is QC and QB naught. QC and QB naught. And KA is QB naught and QC naught. Okay? So the reason we do that, and the reason I do that, is because now we know what's on the J's and the K's. And once we know what's on the J's and the K's, we know what the flip-flop's going to do. Right? And that's the goal here. What we're trying to figure out is when I fire this thing up and start clocking it, what's going to happen on the outputs. Right? That's what we want. And we know that by what's on the J's and the K's. And we know what's on the J's and the K's because we've just mapped it out, right? So JB is hooked up to QA naught. So that means JB is going to be whatever QA naught is. So that's why I have JB equals QA naught. Okay? So, once you have this, you can fill this out, right? Because, for example, this is QB or QA naught. Well, what's QB and QA right now? They're both 0. So this is going to be 0 or 1, right? Because QA is 0, which means QA naught is going to be 1. And if you have 0 or 1, what does that equal to? Equals to 1. So we know JC is going to have a 1 on it. KC is equal to QB naught, right? KC is equal to QB naught. Well, if QB is 0, what is QB naught going to be? Maybe 1. Right? So now, the C flip-flop, right, JC and KC, both have 1s on them. So what's that flip-flop going to do? It's going to toggle, right? Because 1, 1 is toggle. Right? So now we look at the B flip-flop, right? The B flip-flop. JB is equal to QA naught. KB is equal to 1. So we know KB is equal to 1, so I can just put that here. QA naught, if QA is 0, QA naught is going to be 1. So it looks like the B flip-flop is going to be toggling as well. So what's this one going to do? Oops. So QC naught and QB naught is J, oh, that's, where am I? Oh, A, sorry. A is QC, sorry for the little mistake there. JA is hooked up to QC and QB naught. I know QC is 0. And if I've got a 0 going into an AND gate, I know that's going to be 0. And then KA, which is this, is QB naught, which is going to be 1, and QC naught, which is going to be 1. I've got 2 1s going into an AND gate, so that's going to be 1. Okay? Now, this is half of everything you need to know. Right? So for every count that you have, you know what's on each J and each K. It's been mapped out because it's right there in front of you. You can see it, right? You can see that JB is equal to QA naught. So we're just cataloging all of this stuff. We know KB is 1. So once you have the count, okay, once I have this, that gives you this. Okay? This is a 2-step process. This is step 1. When you have the count, you know what's on all three flip-flops. Okay, does everybody, we're good so far? Okay, once you know the count, you know what each J and K is hooked up to, you know what the current output is, so you can figure out what all these things are. So just again, very quickly, I had QB or QA naught. So this is 0 or 1, right? And if you have 0 and 1 going into an OR gate, we know the output's 1, right? So that's why this is 1. So again, the count gives you this. Okay? Step 1. Step 2 is you use this to get the next count. Because now we know what's on all three flip-flops. So if we know what's on the flip-flops, we know what the output is going to do. Right? Once you know what's on the flip-flops, you know what the output's going to do. So what's the C flip-flop going to do? Right? The C flip-flop is going to toggle. So you go to QC. QC is currently 0. So if it toggles, what's it going to be? It's going to be 1. Right? What's the B flip-flop going to do? It's going to toggle. So that's going to be 1. And what's the A flip-flop going to do?
Reset.
It's going to reset, which means Q is going to be
0.
Yeah. Let me be a little more economical with the space here. Okay? So, step 1, the count gives you what's going to be on the J's and the K's. What's on the J's and the K's gives you the next count. Okay? That's step 2. The count gives you what's on the J's and the K's. What's on the J's and the K's gives you the next count. That's it. That's all you need to know. Now you just do it again. Okay? That's it. This gives you that, and that gives you this. That's all you need to know. Now, we just need to do it again. And we need to do it again and again because that's going to give us the count. Eventually, the count's going to repeat. Once it does, then we're done. Right? So, the count gives you what's on the flip-flops. What's on the flip-flops gives you the next count. So now, let's find out what's going to be on the flip-flops on the next clock cycle. So, QB or, well, QB is a 1. So 1 or anything is 1. So I know this is going to be 1 right away.
0.
QB naught is going to be 0, right? Because QB is 1 now, which means QB naught is going to be 0. We're good? Everybody's good? Okay. QA naught is going to be
0.
1, because QA is 0, right? So QA naught is 1. This is always 1, because it's tied to VCC. QC and QB naught, well, QB naught is going to be a 0, so a 0 going into an AND gate is a 0. And QB naught is 0, so that's going to be a 0. Okay? So remember, the first count gave us the first flip-flops. The first flip-flops gave us the second count. We're done. So now we're just repeating the process, right? So the next count gave us the next J's and K's. So now the next J's and K's is going to give us the next count. Okay? We're just doing the same 2 steps that we did. Sorry if I'm repeating myself, but the count gives you what's on the flip-flops. The flip-flops gives you the next count. Repeat, right? So we took the next count. We got what's on all the other flip-flops, right? So now this is going to give us the next count, right? So the C flip, what's the C flip-flop going to do?
Set.
It's going to set. We know that here. That's why I kind of put this up here to the side. So if you have 1, 0 on J and K, that's a set. So we know Q is going to equal 1. Right? What's the B flip-flop going to do? It's going to toggle. What's the A flip-flop going to do? No change. The answer's on the board. No change. So it was 0. It's going to stay 0. Okay? Now, I'm just doing what we've already done twice. I'm going to use the next count to figure out what's going to be on the J's and the K's for the next count. Right? So this is QB or QA naught. QA naught is going to be 1, so this is going to be 1. QB naught is going to be 1. That's good. QA naught is going to be 1. This is going to be 1. This is going to be 1. QC and QB naught is going to equal to what?
1.
Right? Because QC is 1. QB naught is 1. So we've got 2 1s going into an AND gate, so that's going to be 1. And then QB naught and QC naught, well, this is going to be 0 and 1, so this is going to be a 0. Okay? So, this gave us 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 this. And this is going to give us our next count. So, what's the C flip-flop going to do? The C flip-flop is going to toggle, which is going to make QC go to
0.
It's just doing what it's told. It's a JK flip-flop. Okay, the B flip-flop is going to toggle.
1.
The A flip-flop, set. So that's 1. So far my counter is going to go 0, 6, 4, 3. We don't know, so we keep going, right? So now this gave us this gave us this, and now this is going to give us this. So QB or, well, QB is 1, so I know that's going to be 1. QB naught is going to be 0. QA naught is going to be 0. KB is VCC, so it's always 1. When you have a table like this and you see a 1 or a 0, you can just put them all in. This is going to be QC and, well, QC is a 0, so that's going to be a 0. And again, I'm just using our Boolean theorems here. If you have A and 0, we know that's 0, so that's all I'm doing. And QB naught and QC naught, that's going to be a 1 and a 0, so this is going to be 0. So what's the C flip-flop going to do?
Set.
Answer's on the board. Set. What's this flip-flop going to do?
Reset.
Reset. What's this flip-flop going to do? No change, right? 0, 0. No change. It was a 1, so what's it going to be next time? 1. So far, if I build this counter and I fire it up, it's going to go 0, 6, 4, 3, 5. So we keep going. We don't know. So QB or QA naught. So that's 0 or 0. So that's 0. QB naught is 1. QA naught is 0. This is always 1. QC and QB naught, that's going to be a 1, right? Because QC is 1, and QB naught, which is 1, because QB is 0. So that's a 1. And QB naught and QC naught, that's a 0 and a 1, so that's going to be a 0. So, do you see how we're just repeating the same process over and over again? That's why I said this is more tedious than it is complicated, because this gives you that gives you this. Repeat, 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 repeat. So, we're at 5 now. So, this is going to reset. This is going to reset. This is going to set. So that's 1. We're getting down there. It's going to have to repeat soon because there's only 3 bits. So QB or QA naught, that's going to be 0. QB naught is going to be 1. QA naught is going to be 0. This is going to be 1. And QC and, so this is going to be 0. And QB naught and QC naught, that's going to be 1 and 1, so that's going to be 1. So I think we're done. Because what are all three of these flip-flops going to do? They're all going to reset, right? Which means they're going to go to 0, 0, 0. So after 1, you go back to 0, 0, 0. Okay? Right? Because this is going to be 0, 0, 0 because all three flip-flops reset, but we already know what happens after 0, 0, 0, right? It goes to 6. Right? So as soon as you get your repeat, you just do this. So this counter is going to go 0, 6, 4, 3, 5, 1, 0, 6. Why is it doing that? I don't know. But that's what it's going to do. So if you want to look at it in terms of the state diagram for that counter, it's going to go 0, 6, 4, 3, and after 3 we go to 5, and after 5 we go to 1, and after 1 we go to 0. So this counter has 6 states, so the modulus of this counter is 6. So it's a mod 6 counter, and the states it's going to go through is 0, 6, 4, 3, 5, 1, 0, 6, 5, 3. So if you build this in coordinates on your proto board, and you put all the presets and clears to high and build it synchronously to count, and you start counting it, you're going to see this count come up. And it's going to go over and over and over again. Now, what states are missing? What states are not in this counter?
2, 7.
Hmm?
2, 7.
So 2 and 7 are missing. So let's say that we wanted to just double check to make sure that we knew what would happen if the counter mysteriously through a glitch or power outage or whatever came up and it was in state 2. How would we find out what it did after state 2? The exact same way that we've been doing it, right? If you want to know what happens after 2, just put 2 in the output, right? So if you want to know what happens after 2, put 0, 1, 0, which is 2, and go through the same exercise again. So QB is 1, so this is going to be 1, 0, 1, 1, 0, and 0. So the C flip-flop is going to set. This one's going to toggle. And this one's not going to change. So 2 goes to 4. So the way you indicate on that is you go 2, goes to 4. So if it comes up at 2, it's going to go to 4, and then it's going to continue its sequence. It's going to go 2, 4, 3, 5, 1, 0, 6, 4, 3, 5, and so on and so on and so on. So if you want to find out what happens if it comes up at 7, just put 7 in there, and you'll find out very shortly. Because QB or, well, that's 1, 0, 0, 1, 0, 0. So the C flip-flop's going to set. This is going to reset. And that's not going to change. So 7, as it turns out, goes to 5. Now, if you're doing something like this, the reason you want to keep track of the unused states is to make sure that if the thing came up at 2, that you didn't have a weird situation where you had 2, 7, back to 2, because then it would just be stuck in a loop and your counter would never count. Right? So you just want to make sure that you know what happens in the unused states. Okay? Any questions? So you have the table in your lab. The table's already done for you, but the whole idea is you pick a count. I could have started with 4 and I would have ended up with the exact same answer. I just used 1 as 0, 0, 0 arbitrarily because it's a natural place to start. The count gives you what's on the J's and the K's. What's on the J's and the K's gives you the next count, and you just repeat that process until you've mapped everything out.